In this video, we will be looking at the properties of logarithms. In the last video, we were just talking about some of the basics, looking at the graphs and how to change between exponentials and logarithms. And this section is putting together a handful of properties that we'll use to solve equations. The applications problems we'll be seeing going forward use logs to solve an exponential equation and exponentials to solve a logarithm equation. So we kind of go back and forth between the two. The first property we'll look at is the product rule. It's showing us that if we have two numbers that are multiplied together as the argument, or again, what we're taking the log of, we can separate them into two logs with the same base, and we use an addition sign between them. Here's an example written down here where, kind of going in the opposite direction, we have the log base 2 of p to the third power and the log base 2 of q. Both of the bases have to match for us to utilize this property, and we can combine them together into a product like this. I'm going to go through the proof of this. So to prove this, log base a of m n equals log. Okay, the first thing that we'll do is we're going to let log base a of m equal a different variable. Let's call it u. And we're going to let log base a of n equal a different variable. Let's call it v. Now we learned how to change into exponential form. So rewriting both of these in their exponential form, I have a to the u power equals m and a to the v power equals n. Okay. So starting on the left-hand side of what I'm trying to prove, this is the same as using the substitution that I have right here and here. I'll rewrite this as log base a of a to the u power instead of m times a to the v power instead of n. When we have two exponents and the bases are the same, we can add the exponents together because these are being multiplied. So this would be a to the u plus v. And then I want to know how to simplify this. Do a little work here on the side. Suppose I have log base a of a to the u plus v equals something, right? Rewriting this as an exponential, I have a to the something power, I don't know what it is, equals a to the u plus v. Again, I'm changing to exponential. I'm saying this is the base, this is the exponent, and this is what it's equal to. Well, looking at this equation that I have here, I can see that the question mark is going to be u plus v. So this simplifies to just u plus v. And then going back to our original substitution, we can change this to log base a of m and log base a of n. Our second property is the law of coefficients. And similar to what we were doing before, we are going to have the two variables split up, and there's going to be a subtraction sign in the middle of them instead. This is really sort of an extension of multiplication, because if I have a quotient m times n, it's the same as m times 1 over n, or we can think of that as m times n to the negative first power, right? So here's an example. We had taking the log base t of 8 over w, and I split that up into two separate logs, the log of 8 minus the log of w. Let's do the proof for this one. I'm going to start by taking the log of one of the variables. I'll just start with log base a of m. And then I can rewrite this as log base a of, I'm going to take m and I'm going to divide it by n, and then I'm also going to multiply by n. So technically the n's cancel each other and I would be back just with m, but I'm writing it this way so that I can use the product rule from the last example we saw. I have a product now, right? I've got this number being multiplied by this number. So I'm going to separate them. So I'll write this as log base a of m over n plus log base a of n. On the left-hand side, I have log base a of m. So now what I'll do is I'm going to subtract this from both sides. And I get log of m minus log of n equals the quotient that I started with, right? This third example is also an extension of the product rule. This is saying that if we have a number that's being raised to an exponent, we can take that exponent and we can bring it out into the front as multiplication. So in the example, we can see that the negative 3 that was an exponent was brought down into the front and multiplied by the log in the front. This one's pretty easy because it comes right from multiplication with the product rule. So let's start with the log of m to the p power. This is the same as m times m times m, multiple times, right? In fact, p times. So using the product rule, we could say that this is log base a of m plus, just taking each of those m's that are multiplied and changing it into a separate log that's added together. And again, there are going to be p sets of these. So instead of saying I have, let's say, x plus x plus x plus x, I could just say that this is 4x, right? So simplifying this, this is going to be p sets of log a of m. All right, let's look at a couple examples. We use the laws to separate or compress logarithms. And so in this first example, what we're doing is we're separating them into sum and differences. So For letter A, the first thing that we're going to do is anything that's in the numerator that's multiplied together will be added. Anything in the denominator will be subtracted. And we keep the log bases all the same. So this will be log base A of x squared plus log base A of y to the fifth minus log base A of z to the fourth. Then we can take each of the exponents and bring them down into the front and multiply them. And that would be our answer for the first one. Looking at the second one, we have, I'm going to rewrite this to start. I have log base A of a squared b over c to the fifth all to the 1/3 power, right? When you have an exponent multiplying by another x, or raised to an exponent, you multiply those things together. So I'm going to switch all of these to be fractional exponents. Let's rewrite this as log base A of a to the 2/3 and b to the 1/3 over c to the 5/3. Now we'll continue like I did in the last one, separating all of the items in the numerator as a product, so they'll be added, and then anything in the denominator will be subtracted. So let's see, we'll have log base A of a to the 2/3 plus log base A of b to the 1/3 minus log base A of c to the 5/3. And then again, I can take all of the fractions and bring those exponents down into the front. And then this first part right here, log base A of A, that's just going to be 1, right? It's asking us A raised to what power is equal to 1. So technically we could simplify that part to be 2/3 plus 1/3 log of B minus 5/3 log of base A of C. Oh, I forgot the base here. And here, right? You need to put the base, otherwise you think that it's base 10. All right, last example. I think that there's a typo in this one. I think that this should be the base. I think it should be down here. So this should be log base B of a y to the 5th over m cubed and n to the 4th. So we'll split this up into log base B of A plus log base B of y to the 5th minus log base B of m cubed, and then also minus log base B of n to the 4th. Anything in the denominator gets subtracted. And then bringing the exponents down. That's our final answer. So again, this is how we use the 3 laws to expand different logs. Most of the time, though, we actually go in the opposite direction, where we are compressing all of the items and we're putting them together in a single log so that we can change to exponential form. So you're more likely to see something like this. So I'm going to start by taking any number that's multiplied in front, moving it up as an exponent. So I'd have log base b of x to the fifth. The log base b of y stays the same. And then this one will be log base b of z to the 1/4. Anything that is positive stays in the numerator, and anything that's negative goes down to the denominator. So we'll put this together in a single log with x to the fifth and z to the 1/4 in the numerator and y in the denominator. A couple more special cases that we have. These might seem sort of obvious. This is saying that when you have log, the base matching the base of the log and the base of an exponent, that the final answer overall is just going to be this exponent that you're taking. Thinking about this in terms of changing to exponentials, we're saying this base raised to this exponent equals this whole thing. So that kind of makes sense. And so then simplifying this, this would just be 8. ln is log base e, so the base matches here, and so this answer would be negative t. And then also when we don't write the base is implied to be 10, and so this answer is going to be 3 times k. We're just saying that it's going to end up equaling what the exponent is. And then for this last example, we're looking at when you have the base of an exponent being raised to a log that has the same base. Similar idea. Let me show you a proof for this because this one looks a little bit more tricky. Let's prove this. Let's let m equal log base a of x. So what we're looking at is a to the m power equals x. I just did a variable substitution here, and I'm calling it m instead, right? So we know that a to the m equals x because that's taking this and changing it to exponential form, right? A, here's the base, here's the exponent, a to the m is equal to x, so that's what I'm writing here. And then just taking what you originally had and substituting it back in. Instead of writing m, we write log base a of x. We get what we're trying to prove. Kind of a little silly idea here. It's really just a definition in disguise. The point is that if you have something like this where the base is a number and then it's raised to a log as the exponent and the base of the log is the same, that your overall answer is just going to be the argument, in this case, k. Again, remember that the base of natural log is e, so technically I have e sitting right here, so my overall answer here is going to be 5. And then similar, when I don't have a base written, the base number is implied to be 10, so the answer here is going to be 7t. All right, again, these are just some of the rules that we use for solving equations that have logs in them, and we'll be doing that in the next section. Thanks for watching.